Hello, hello, Wave Motion 2, welcome. If you're a second year, this is just like a recap, jump in, use it however. If you're a first year, then welcome, learning for the first time, waves. Right, hopefully actually no one's learning this for the first time. It's electromagnetic waves. You should know it, it's pretty basic, you've learned it at GCSE. They're actually quite interesting in how they work, but ultimately what you need to know now is just approximate values, applications, and the regions of the different spectrum. You'll know that. And then Malice's law about polarization you won't know, because you won't know what polarization is. Maybe you do, maybe you don't. We'll see. Right, so an electromagnetic wave is pretty much what it says on the tin. It's an electromagnetic wave. So it is the waving of the mutually perpendicular electric and magnetic fields. Now, what it means by mutually perpendicular is it means that they will always be perpendicular to one another. No matter how you manipulate one, the other will bend accordingly. So if I pluck the electric field, or I pluck the magnetic field via the action of moving something with an electric charge, or moving something with a magnetic field, then it will cause a electromagnetic vibration, which is an electromagnetic wave. Now, most of these we just can't see. Some are even so low energy that we can't even detect. But there's a full range of them, as you know. It's called the electromagnetic spectrum. It's big. So, basically, it works, and we see it all the time. Like, look, there, a light. The light is basically an electron flying across a gap. Because it's electrically charged, it's plucking all the electric field. Because it's moving an electrically charged, it's plucking a load of magnetic field. And as a result, it causes a vibration, a big brrrm, like that. And that will vibrate all the way throughout. And that's an electromagnetic wave in the form of visible light. Yep. These are the different regions. It goes radio waves, microwaves, infrared, radiation, visible light, ultraviolet, X-rays, gamma rays. That's the song. Remember it. These approximate regions, all the way to 10 to the 8 meters, all the way down to sort of 10 to the 1, 10 meters. That's a radio wave. Bit of an overlap with microwaves, sort of a meter down to a millimeter sort of range. Infrared are in the sort of millimeter down to a micrometer sort of range, and then the few hundreds of nanometers in between infrared and ultraviolet is this visible light. Now, these ones you should be very aware of. You need to know these upper and lower limits of 700 and 400 and be able to identify. If someone says, oh, it's 300, well, stupid, don't say 300. If it's 500 nanometers, for example, you should be able to say, oh, what's that about yellow-green? Like, you should be able to work these out. More like greeny blue. Well, you should be better than I am at that. That was poor. And then ultraviolet is in the up to 10 to the minus 8 range, and then you can see the rest. Now, you'll notice there's a huge overlap here between X-rays and gamma rays. That's about functionality and production. So if X-rays are produced using an X-ray tube, and gamma rays are usually produced from radioactive or huge energy events. So if we say it's being produced like this or being used for X-rays, we'll call it an X-ray. If we're looking at radiation, if we're looking at stars, we're looking at light coming off of high energy events, we'll call it gamma ray. But there is some disparity in what they are. Like if it's really high energy, we'll always call it gamma ray. If it's just above ultraviolet, we'll call it X-ray. Anyway, you need to be aware of those. You also need to be aware of all of these. I'm not going to go through the whole list, but these things, approximately how each thing's made. So like I just said, gamma rays from radiation, radioactive nuclei, and what we detect them in, an ionization chamber, and practical uses like sterilization or medical imaging or medical treatment, such as radiotherapy. You might think, what's an ionization detector? You've just chucked that out there like you've never said it before. We will do a lot of work on them, but they're effectively like cloud chambers, aren't they? You just either detect or watch the path of a very high energy bit of projectile, knocking all the electrons off of something, ionizing it, and then picking up those electrons or picking up that net change in charge. That's an ionization chamber. Infrared is hot bodies, not like Megan, whatever her face was from that film, but like hot as in thermally warm. Make a note of that list, or just take a picture of it, or don't. It's up to you, isn't it? You're doing the A-level physics. You might just already know it. You might think, oh, I'll just have that in my mind. Or you might think, learn it later. But I think, make a note of that list, or take a picture, whatever. So radio waves, oscillating electric charges, they produce a slight, languid, big wave, but very low energy. They can be picked up by causing the same result in another thing. So let's say I've got a mast here, there's electrons vibrating up and down in it, that creates this wave, the wave eventually gets to a mast, and then the mast, as it passes through a detector, the detector's electrons will move in the same way that one's will, and we can pick up the signal from that. Microwaves, very big overlap between radio waves. I know that really didn't make it seem like it, but there is a big functional overlap between radio waves and microwaves. We differentiate them by the source. The radio waves are produced by tuned circuits, little electrons dancing up and down. Microwaves by magnetrons, which is like a magnetocyclotron type thing. You might not know what that is, but you should look it up, and I'll tell you about it in class in more detail. But it's rotating magnetic fields or vibrating magnetic fields. And infrared is produced by, as I said a minute ago, warm things. Now, that even the coldest things produce a bit of infrared, really. Obviously not like minus 273.15 Kelvin, like absolute zero cold, but like ice. Ice produces infrared. Not a lot, but it does. So the greatest application for microwaves is actually in communications and radar. Right? So using microwaves is predominant use of microwaves is mobile phone circuits. But the thing you'll think of most when you think of microwaves is cooking. Infrared, anything with a 0 Kelvin temperature will produce some infrared. Now, 0 Kelvin will produce nearly none, and anything higher than that will produce some, but it will be extremely low value. But anything with a temperature will produce infrared. Some information there. Read it. Why should I read it? Why should I read it? You read it. Do some work. Right, ultraviolet light. Yep, this is the 10 to 400 nanometers range. Given the name ultraviolet because it is ultra, extra, added on from violet. So it's like more high frequency than violet, or lower wavelength. Now it's broken into A, B, and C, long wave, medium wave, and short wave, which have those values. Now those values, good to know. Good to know those values. Useful. What's the function of these things? Well, UVC is nearly all absorbed by the atmosphere. UVB, most of that is absorbed by the atmosphere, but about 2% gets through, and that's really essential because that does things like break down bilirubin in the skin of jaundiced infants, or produce vitamin D in all the rest of us. Unless you're a natural redhead, then you produce your own vitamin D. Is it a myth? I don't know. My wife's always said it to me. And UVA is just sort of like the basic, pretty low energy UV, but nearly visible light. That's something that a lot of animals see in. A lot of birds, a lot of insects actually see in that range. And a bit of visible as well. There we go. X-rays are produced when high-speed electrons collide with a metal target, such as tungsten or molybdenum. So I'll talk you through how those work when we study X-rays in end of second year. Basically, electron accelerated really fast, slaps into something, and then through some magic physics, X-rays are released. And we use them for imaging, don't we? Gamma rays, high energy, highly penetrating radiation, radioactivity, radioactive nuclei. They're the things that produce this kind of thing. You know this stuff. I'm moving on. It's sterilization as well. We use it for sterilization. Not like of criminals who committed sex crimes. We use chemicals for that. But sterilization like of medical equipment. So, what are the properties of EM waves? Right, all of them travel at the speed of light, which is approximately 3 times 10 to the 8 meters per second, 300 million meters a second. Well fast. That will change if it's out of a vacuum. So if it goes into air, it will change. It'll have a different speed, and there is a slight variation between different frequencies and how they permeate through. So the speed of light is a constant in a vacuum. If you mess with that prerequisite of being in a vacuum, it isn't the same. But you don't need to worry about that. It's 3 times 10 to the 8. Remember that. You don't even need to remember it. It's in the formula book. It's continuous. It's not chunked at all. It's not like you have things of a certain value and then a big gap and then other sections of a different value. So it's a completely continuous spectrum. Radiation with the same wavelength and frequency have the same properties, but they are differently named according to their origins. Like we were saying about some aspects of radio and microwave, they could be exactly the same for all intents and purposes, but how they were produced defines what they are. And there is an overlap between X-rays and gamma rays, e.g. Right. All EM waves transfer energy from one place to the other, so they are progressive waves. They're transverse and can therefore be polarized. Now, we haven't learnt what polarization is yet, but I will talk about that in a minute. They obey the laws of reflection and refraction and can be superposed to produce interference and diffraction effects. Now, once again, we don't know what those things are yet, but I'll tell you later. And they have zero electric charge, unaffected by electric, magnetic, and gravitational fields. That's not true 100%, but by and large, it's pretty true. In fact, cringe. Yeah, it's true, not true. It's not true. The zero electric charge thing, but they are affected by electric, magnetic, and gravitational fields. Polarization. Hello. Welcome again. Polarization. An unpolarized wave is one in which its vibrations in the electromagnetic field are all over the shop, just at right angles to its direction of travel and all over the shop, kind of like this. Right? This is unpolarized because there's no net directionality of this vibration. There's a net directionality of its direction of propagation or direction of travel, but its vibrations are all over the shop. A plane polarized wave is one that has its vibrations locked into one plane of oscillation, hence the term plane polarized. So wave A, just going up and down, it's vertically plane polarized, and wave B, just going side to side, it is horizontally plane polarized. They're both going in the same direction though. Transverse waves can be polarized, but longitudinal waves cannot be polarized because their direction of vibration is in the direction of their propagation. So if we chop that off, stop them oscillating in one direction, we just stop the wave. So a polarized longitudinal wave is just a stopped wave. So we say that it can't be polarized. So we can polarize light using Polaroid filters, which you may notice there's a little asterisk, which is basically saying Polaroid is a brand name. Unpolarized light becomes polarized after it has passed through a piece of Polaroid if a second Polaroid with the axis is in a different orientation. It will affect whether light can get through or not. Now imagine we pass it through a Polaroid, unpolarized light, just like this down here, and then it moves through a vertical polarizer, then we get vertically polarized light. If we move it through another polarizer, it will depend on the orientation of that polarizer as to what gets through on the other side. If, for example, if we rotate the second one, it will reduce the intensity to the point where if it's complete right angle, the light will just be completely absorbed. Nothing will get through. There you go. And there's also this thing called partial polarization, which is something that happens when